So number 8, what else? Yes, ma'am? Number 11. Yes, ma'am? 12. Yes. 7. Yes. 9. Yes.
1.
Yes. 10. All right. I know we have 60 minutes today, so I'm gonna try and be as eloquent and as complete as possible. I'm gonna do these probably in this order, if that's okay with you guys. That way, because they don't go from easy to hard here, but they kind of do. Yeah.
I was just gonna say 8 and 9 are like part 1 and 2.
So we have to do those together.
We don't have to, but it's easier that way.
All right. So number 1 is an exercise. It's not really a problem. I will do it, but I want to point out it's written purposely to be vague. It says a horse accelerates to a speed of 20 meters per second in 3 seconds. Can anything be determined about the horse's motion variables from this information? Well, yeah, plenty of things can be determined, but you may not like some of the answers I have here. This problem is not, this exercise is not so much a exercise as it is, do you understand the nature of motion variables and the extent of what you can do with the information given? We are told 2 things, 20 meters per second in 3 seconds. Can we determine anything about the motion variables? Yes. At the end of the interval, the object was traveling 20 meters per second, and that interval lasted 3 seconds. Can we determine anything else? No. Now, that might or might not be what you want to answer here, but with only 2 pieces of information, we really can't determine anything else. We don't know whether the object was slowing down or speeding up. We just know that it accelerated to a speed of 20 meters per second. Now, you may make an assumption, and that assumption could be wrong. You would have to have a reason to make an assumption. So some of you made this assumption, that the horse accelerated from rest, assuming it was speeding up, and assuming it started while not moving. Now, you could make that assumption. You'd like to have good reason for it, but you could make that assumption. If you did, well, then you could determine the other 2 pieces of information. Those would be exercises. But that would be assuming something. That would be creating a piece of information that was not explicitly stated in the problem. Be careful how you apply that kind of rule. If you're going to say that something started from rest, have a clue as to why you believe that to be true. Is there something in the problem that states that gives you that impression? And be careful about the word accelerate. It doesn't mean speeds up, right? It means changes their velocity. Yes, ma'am.
So for answering the question, would you put the first, there's 2 questions for that one. Would you put the first one just to be like, just the velocity, just the velocity and time to be determined? Because I put like the other, like the initial velocity, acceleration, and final velocity could be determined assuming it starts from rest.
That'd be the perfect way to answer that question. Yeah. And you've really answered both parts of it by saying that, and that's fair. I put this as a problem because it's, believe it or not, it's all over your book. I want to make sure if you did answer any of the questions that are out of the book as practice, this is what they're looking for here. But also it's for me to convey to you that as exercise goes, you can't solve anything until you have 3 of these pieces of information or something that conveys more information that may be explicit in the question. Does that make sense to all of you? All right, that was all number 1 was about. So I think that means I move on to number 7. All right, number 7. This is where we start getting into stuff, I think. A cyclist traveling at a constant 10 meters per second passes another doing 5 meters per second. The second cyclist, not wanting to be beat, accelerates constantly at 1 meter per second squared until they eventually catch the first cyclist. How long do they have to maintain this acceleration? How fast are they going when they reach the first cyclist? And how far have they traveled? So clearly, for this to be a problem, we are assuming that one of the cyclists is at a constant speed and the other one is capable of catching up to them because they are accelerating. Does that make sense? All right. This is the police officer problem, and the only difference between this problem and the police officer problem is that both cyclists are moving at time 0. So let's look at cyclist 1 versus cyclist 2. Cyclist. and consider the information that has been provided in both cases. I also kind of believe in drawing pictures for our problems. You may not be the kind of person who does that, but I would encourage you to start. When we get to the next unit, drawing a picture is going to be required. So it's good practice to start drawing them now. They don't have to be complicated. For me, this is going to be a cyclist. And here's the other cyclist. What I want to do in my picture is give myself points of information regarding the direction of events. So for example, at time 0, this cyclist is traveling at 5 meters per second, and this cyclist is traveling at 10 meters per second. That's time 0. Now, both cyclists are going to travel in this direction and will eventually hook back up where this cyclist will still be traveling 10 meters per second. But I suspect that this cyclist will be traveling faster. And the only way that they're going to catch up is if they eventually go faster than them so that they can overtake them. They will travel some distance, but it's going to be the same for both. Right? They're going to start at the same position, and eventually the slower cyclist will speed up and catch the second cyclist. And I'm going to make everything that's in this direction positive. I think drawing an arrow on a problem and explaining to your reader or your grader or yourself what direction things are positive will be of great use to you in the future, something I will require on diagrams later. So it's not a bad habit to get into. All right, so let's start with the given information. Cyclist, we'll make this cyclist 1 and this one is cyclist 2. Cyclist 1 has an initial velocity of 10 meters per second and a final velocity of 10 meters per second, 0 acceleration. So we know the kind of the conditions of this cyclist. They're traveling at a constant speed. And that kind of predicates that all we can do with this cyclist is say that. Nothing else we can say about that cyclist. And that's because they're traveling at a constant speed. Is that too low for you guys to read? That better? All right. Cyclist number 2, however, has an initial velocity of 5 meters per second, but is accelerating at 1 meter per second squared. We don't know anything else about this cyclist, their final speed or time or displacement. But since we're comparing this to another problem, I recognize that I could assemble a relationship that uses these two pieces of unknown information, but link them up with the information that I have for the first cyclist. Both cyclists travel the same displacement, and both cyclists do so in the same amount of time. Does that make sense? All right, so I'm going to look at delta x equals 1/2 a t squared plus v naught times t. Now, I see a pathway to solve this problem, and we've done one just like it before. If you want me to continue, I will. Is there anybody who would like me to complete this question? All right, so I will notice that they are both solved for displacement, and although, I think I'd like to solve for the displacement, it's easier for me to do substitution with what I have already. So I can say 10t equals 1/2 times 1 t squared plus v naught times t. All right, so I want to solve for time here, and I think the only way to do so is to do that. I get two answers for time. Subbing out the factoring out one of the t's, I get t equals 0, and t equals 5 divided by 0.5, which has got to be 10 seconds. So obviously one of these t's are more important than the other. We asked the math to show us when the two cyclists were at the same position. It told us, time 0, though, is not the one I want to use. I want to use 10 seconds. So to figure out how far, I'm going to go back to here, and that gives me that delta x is equal to 100 meters. Yay. He was moving too, though. 10 meters per second is just a little over 20 miles an hour. As a person who cycles myself a little bit, I find it difficult to get to 20 miles an hour. I know some cyclists who routinely pedal at 25 miles an hour all the time, but his final speed is over 30. That's probably very challenging to maintain for a cyclist to do, but I'm sure they can do it. I don't know. I can't, but maybe they can. I'll try harder. So number 8 next. Alrighty, number 8. And 8 and 9 you said are together, so this is the 2 trains problem? All right. There are a variety of ways to do this question. Number 8. Number 9, good luck. I may or may not do number 9. But number 8 we will. When I read this problem, I have a train here and a train here. Okay. They are separated by, 1,000 meters? And this train's going this way, and this train's going that way. Now, they are clearly going to meet in the middle, right? There's no doubt. Even if one stops, the other one's going to hit it. So they're going to meet somewhere in the middle. I know that they're both starting out at 20 meters per second. And one of the trains is going to experience an acceleration of 0.5 meters per second squared. It doesn't matter to me which one of these trains is train 1 and train 2. So left or right, which one is going to be slowing down? Is your right and my right the same? Yay. So 0.5 meters per second squared. That's the direction of the acceleration. There are many ways to decide how to do this problem. If this were last year, I would present a way that I like better than what I'm going to do this year. Last year, what I would have done, because students have so much difficulty with positive and negative when it comes to direction, I would have picked a place in the middle and said that this train goes delta x, and this train does 1,000 minus delta x, and made it 2 one-dimensional problems where everything's happening in the same direction. I'm not going to do that this year. And the reason is because I would like my mechanics students to have a more robust understanding of why the variables work the way they do. So I'm going to do what I've been doing all year, which is treating all problems as if they can be solved using a common set of variables. And if you don't know what I mean by that, please follow along. This is a number line. Which train is at the origin at time 0? You pick, left or right. It makes no difference. Left is at the origin. So we're saying this is 0. So at time 0, this train's initial position is 0. And at time 0, this train's initial position is 1,000. Right, we're on a number line. Everybody okay? All right. What direction is positive? To the right or to the left? Based on what we've just drawn, we have established that this has to be the positive direction because we are at the positive 1,000 meter mark on the right. Everybody understand? Okay, let's begin the problem. Train 1, delta x, v naught, v a t. Train 2, delta x, v naught, v a t. It is important that we recognize the vector portions of this problem. But it's also important that we do one more thing. My watch just told me to stand up. I guarantee I have not sat down since the bell rang for lunch. And it's not like I've been not walking around. I don't like that because I'm going to lose credit for this hour. And I don't know whether I'm like, should sit down real quick to make the watch think I'm sitting down. I mean, I don't know what really I'm supposed to do. Right now, I'm just waving my arm around, flailing, hoping it thinks I'm standing up, which is why I'm gesticulating with such amazement. But I'm frustrated. Getting my rings closed is a valuable thing to me because I'm in a competition with my daughter all the time. And I have not closed all of my rings in 870 days. Not breaking that streak just because of her. She breaks that streak all the time. So, frustrating. Stupid watch. Delta X, oh, and all that's in the video now. There you go. Yay, guys. X minus X naught. Right? That's what delta X stands for. Change in position. So, let's figure out the train on the left. That's going to be X minus 0. Initial velocity appears to be positive 20 meters per second. Final velocity, positive 20 meters per second. Acceleration, 0. Time, don't know. Keep going. All right. Train on the right, delta X is going to be X minus 1,000. Right? Its initial position is positive 1,000, but delta X is X minus X naught. So everything good there? All righty. Initial velocity, minus 20 meters per second. The velocity for train 2 is to the left, so its velocity is negative. Final velocity, don't know, but acceleration is to the right, so that's positive 0.5 meters per second squared. The trains are going to meet at some X in the middle. That's the final position, which should be the same for both trains. And they will get there at the same moment in time. So with that being said, the train on the left, X minus 0 equals 20t. The train on the right, X minus 1,000 equals 1/2 a t squared minus 20t. That's it. Problem solved. I mean, not solved the way you would like it, because you just still don't know what x and t is. But we've done all the physics. The rest of this is algebra and arithmetic. But the physics tells me you've got two equations with two unknowns. Pass this over to your algebra teacher and say, let them do it. But, you know, that's not going to be okay for the test. You can't just circle the two relationships and say, Mr. Shelton, I did all the physics. Now you do the math yourself. So, but we could be done here, ultimately. This is really all there is. Now, if you would like, I will do the rest of the arithmetic. Is there anybody who would like me to do the rest of the arithmetic? All righty. Arithmetic. I'm just going to take that and plug it in for x here. Because x minus 0 equals 20t is just x equals 20t. So 20t minus 1,000 equals 0.25 t squared minus 20t. This is a clear quadratic and is going to be solved by using the rules of a quadratic. I'm going to get everything to the same side. So 0 equals 0.25 t squared minus 40t plus 1,000. I don't know if this factors. So I would probably resort to using the quadratic formula or a calculator. You guys understand that your calculator has the capacity to solve a quadratic by just punching it in. You can use the graphing functionality to get the roots of an equation, whatever. But I'm just going to do it the good old-fashioned way. Negative b plus or minus the square root of b squared minus 4ac divided by 2a. So no physics here, but this is what t equals. That's 40 plus or minus the square root of 1,600 minus 1,000 divided by 0.5, which is 40 plus or minus the square root of 600 divided by 0.5. Square root of 600 is what, 22? 23? I mean, square root of 625 is 25, isn't it? No.
4.5.
Is it 24.5? I thought it was 22. Okay, 24.5. So, no, that's easy enough. 40 plus or minus 24.5 over 0.5. God, I would just like to make it 25. It's so much easier. But I'm going to make it 25 for demonstrative purposes. You guys should keep more decimal places in your answer, okay? But I'm just going to do that because that's going to be either 65 over 0.5 or 25, no, can't even add, 15 over 0.5, and I wrote 14, so what's wrong with Mr. Shelton? I don't know. There. And that means this is 130 or 30. Those are my two possible times.
If you use the 24.5, actually, it's also makes it
Okay. 31.
Yeah.
And the other one is,
No, the 30 with 31 and
the other one is what?
I haven't done it yet.
129? All right. So, two different times. Which one's right? Only one of them is right. And I guarantee it's the 31. Now, why do we get two times? I'll explain why we get two times in a minute. But I want you to think about this problem a little differently. You have two times here because the quadratic says there are two times. We asked the problem to tell us when they would be at the same position at the same moment in time. The problem is that the math doesn't know the trains are going to hit each other. All the math knows is that there's two functions that it's comparing, a linear function and a quadratic function. So it's going to produce two possible points where those functions meet. If the trains strike each other, that's when the 31 seconds occurs. But what if they're on two parallel tracks? The one train will miss the other train, slow down, and then come back and catch up to it, right? Because one train is traveling at a constant, the other one's coming towards it. It's slowing down. This one doesn't change, it keeps going, but the other one starts to go back the other direction and eventually catches up. That's what this time is for. If the trains didn't hit each other, then they would have met back up at 129 seconds. But if they hit each other, well, that's the 31 seconds. So which time do we use? We use the 31 seconds. So where does that happen? 20 times 31, which is when x equals 620? That's where they meet. Yay. All right, excellent question. It's the COP question. The only difference about this and the COP question is that you're in a confined limit of distance between each other. But you see the similarities between this one and the police question? At least I hope you do. Any question what we did here or any of the assumptions that we made? Yeah.
So if it's a column like this,
There. Number 11. You drop a rock at the same time as another rock is thrown downwards at 20 meters per second from the top of a 20-meter tall platform. What time interval do the rocks hit the ground? So I think they want to know the time between when the two rocks hit the ground. Does that seem right? I think that's what it's asking for. So I think we just got to figure out how long it takes each rock to go the 20 meters. I'm going to draw it out anyways, and then we'll do part 2 of the problem. I'm going to try. He might be back. So one rock is dropped, one rock is thrown, 20 meters per second, and they are 20 meters above the ground. Is that all of it? All right, so we are just looking for how long it takes each rock to reach the ground. So rock number 1, delta x, v naught, v a t. Rock number 2, delta x, v naught, v a t. And I'm going to make downwards positive. Just easier. So for the rock on the left, it falls a distance of positive 20 meters with an initial velocity of positive 20 meters per second with an acceleration of positive 10 meters per second squared. Second squared, and I'm looking for the time. What's that? The rock on the right, positive 20 meters, initial velocity 0, acceleration negative 10 meters per second squared, and I'm looking for the time. So it's just solving for 2 different t's, t1, t2. They won't be the same. So I'm thinking delta x equals 1/2 a t squared plus v naught times t, so 20 equals 5t squared plus 20t, and 20 equals 5t squared. Questions? Well, I want to do this one, t equals 2. You guys do the other one. I want to do it. It's harder. But you get 2 times, and I want both of them. Do you have them? You have to speak up. I'm old and feeble hearing. 1.82 seconds? 4 seconds? 4.82. There should be 2 times. Yeah, that's a t squared, buddy. Because this one's really not 2 seconds. It's really plus or minus 2 seconds. Right, when you take the square root of every number, you have to take both positive and negative root. I just excluded the negative answer because we can't go back in time. But I'm pretty sure this one had 2 answers, and I'm pretty sure one of them shouldn't be 4.82. Because just think it through. Is it going to take less time for the rock to hit the ground or more time for the rock to hit the ground if you throw it downwards? Less. Yeah. So I don't think it's going to take almost, more than twice as long. That's why I know the answer's wrong. But I think the answer's wrong because you might have a sign wrong. Let's work the problem. Okay, so do I. Like, why you got the wrong answer, but I'll answer your question.
Why the accelerations have different signs if they are both going?
Oh, I think this should be positive. Sorry. I didn't use the positive. It was funny because I used the positive over there, but I wrote the negative down. Sorry. Everybody fix that? All right. Can I keep going now? Because it's still going to give me 2 seconds. And I'm still going to choose the positive answer. And we still don't know which the answer is for this next one. So 0 equals t squared plus 4t minus 4. I divide it out by the 5. Is that okay? This does not factor. I can't think of any 2 factors in 4 that would add together and get 4. except for 2 and 2. Will 2 and 2 work? I don't think they do. Because of where the minus is there. One of those have to be a positive 2 and one have to be a negative 2. And it won't work. So let's go with the old school. Negative b plus or minus the square root of b squared minus 4ac all divided by 2a. So negative 4 plus or minus the square root of 32 divided by 2. Square root of 32, I'm thinking is like, I don't know, 5.6? So this is going to be negative 4 plus or minus 5.6 over 2. Now, I said there's 2 answers, and there is. I should consider both of them. So there's going to be negative 9.6 over 2. That's where you got the 4.8 seconds, but it should have been negative. And the other one's going to be 1.6 over 2, which equals 0.8 seconds. I think that's the answer right there. This is an exercise. This is not a problem. I mean, it's a problem and now you have to use a quadratic formula, but there's really nothing else beyond the quadratic formula. And the quadratic formula does not interest me. But you should be capable quadratic formula students. So moving on, what else happens in this problem? Instead, you drop the first rock and then throw down the second rock at 20 meters per second. How long should you wait so both rocks hit the ground at the same time? 1.2 seconds? Does that seem logical? That's what I would do. Then they hit the ground at the same time. And if you don't know where I got that, it's just comparing those two. The other one's going to only take 0.8 seconds. Drop the first one, wait 1.2, then throw the other one down, and it should hit the ground at the same time. Done. All right. I see that you guys are beginning the wrap-up process. I guess that's why.